Yes, good afternoon, all of you. Am I audible for you?
Yes, sir.
So in the yesterday's class, we have discussed about the mismatch of drain resistance and the effect of that mismatch on CMRR. So I told you there's one more parameter that is going to be a mismatch, and that is also going to affect our CMRR. Ideally, the CMRR will be infinity for a differential amplifier, provided it is working in a double-ended mode. Okay, if you are taking the output in a double-ended mode, we should get CMRR infinity for an ideal differential amplifier. Ideal in the case, in the sense, the two devices are matched in terms of the drain resistance and transconductance. And yesterday we have seen that if at all there is a mismatch in the drain resistance, it is going to affect our CMRR, and the CMRR is going to be a finite value. Yesterday we have done a numerical problem, and instead of getting infinity, I'm getting 86 dB as CMRR. Okay. So like that, there is one more parameter that is called as transconductance, and the transconductance is also going to affect the CMRR. Okay. So CMRR need not be infinity for a practical differential amplifier. The main reason is due to the mismatch in the drain resistance, as well as the second reason is the mismatch in transconductance. So both mismatch in transconductance as well as drain resistance is going to affect our CMRR. So today we are going to discuss the effect of GM, that is transconductance mismatch on CMRR. So for that, take down the circuit diagram, all of you. So in the circuit diagram, you can see that we have given VICM. VICM is the common mode input signal, which is given same for gate of Q1 and gate of Q2. So both gates is fed into a common signal, which is called as VICM. And we have shown a small signal equivalent circuit where I have deactivated all the power supplies. So VDD is being deactivated and it is replaced as ground. And similarly, the constant current source, whatever you can see at the source terminal, is deactivated so that the resistance RSS is directly connected to the ground. RSS is nothing but the resistance that you can see across the constant current source. And for the small signal analysis, we have discarded all the constant current sources and voltage sources available in our circuit diagram, just as the previous analysis. ID1 is a current flowing through Q1 and ID2 is a current flowing through Q2. And I'm taking the output in a double-ended manner. That means the positive end of your device, that is the multimeter, will be connected to the drain end of Q2, and the other end, other drain terminal, will be the reference terminal, just as the previous case. And you can see that VGS1 is the junction voltage across gate and source for the transistor Q1, and VGS2 is the junction voltage across gate and source for the transistor Q2. So how to proceed with? So let us start with writing the expression for drain current ID1 and ID2. In the previous analysis, that is while writing the or while finding the effect of drain resistance mismatch, you have done the equation for ID in terms of RD, isn't it? By applying KVL, you have written ID is equal to minus, VD is equal to minus ID RD. So we were interested to find the mismatch on RD, but now we are going to find the mismatch on GM. So I'll be writing the equation for the drain currents in terms of the transconductance. Okay. So first, let us write the equation for ID1. You know that any drain current of a MOSFET can be written as the product of the transconductance and the gate source voltage. So let us write ID1 as GM1 VGS1 and ID2 as GM2 VGS2. Put it as equation number 1 and 2. Clear, students? Now, as far as the circuit diagram is concerned, the gate terminals are fed with a common signal, that is VICM, and the source terminals are short circuited, which means VGS1 is equal to VGS2 because the gate is common and source is also common. So as both the terminals are sharing, both the junctions are sharing the common terminals, you can write the voltage VGS1 equal to VGS2. Okay, and divide equation number 1 and 2. If you divide equation 1 and 2, what will happen? This VGS1 will cancel. VGS1 and VGS2 will cancel each other because they are equal to each other as per our connection diagram is concerned, right? So now you got the ratio between ID1 and ID2, which is given by GM1 divided by GM2. ID1 by ID2 is equal to GM1 by GM2. Any queries till this equation number 3? So thereafter, we'll try to write the equation for VS. Tell me what is VS. VS is the drop across RSS. From the diagram, it is obvious that VS is the drop across RSS. So what is the current that is flowing through RSS? Apply the junction rule over here and tell me what is the current that is flowing through RSS, students. Yes, please. Nandan Kumar, you tell me what is the total current that is flowing through RSS. Are you there in the meeting, Nandan? You have ID1 flowing through Q1 and ID2 flowing through Q2. So what is the total current flowing through RSS? Please, Pramod. What is the current that is flowing through RSS? Am I audible for you? Then why you are not responding? You can see ID1 and ID2 entering to this particular node. Yes. ID1 plus ID2. Good, Neeta. So ID1 plus ID2 will be the total current that is flowing through RSS. So accordingly, we can write the expression for the voltage drop. That is, the voltage drop is given by VS, which is equal to ID1 plus ID2 into RSS. ID1 plus ID2 into RSS. So the total voltage drop across the source terminal is given by Vs is equal to ID1 plus ID2 multiplied by RSS. That is equation number 4. Okay. Now you have rewritten this. That is ID1 plus ID2 is equal to Vs by RSS. Rearrange it. ID1 plus ID2 is equal to Vs by RSS after rearranging. Okay. And if you analyze this input loop, the input voltage is VICM, which is contributing a fraction of voltage across a junction gate and source, and another voltage fraction is getting dropped across RSS. So you can neglect this VGS as a drop across gate source terminal is very small. We can write VICM as approximately equal to VS. So this you need to assume. Okay, why this assume is validatory? Because the junction voltage across gate and source can be treated as very small in value. Okay, therefore the input voltage will come across RSS. So you can write VICM is equal to VS, please. VS is approximately equal to VICM, equation number 6. And substitute 6 and 5 and write the overall current in terms of VICM. What is the overall current? It is the sum of ID1 and ID2. So ID1 plus ID2 is approximately equal to, in place of VS, you will have VICM. So ID1 plus ID2 is equal to VICM divided by RSS. Okay. Now, as of now, as per this equation number 7, I got the expression for the overall current. Now let us find the expression for individual current in terms of VICM. Students, Are you getting my point? Now I got the overall current in terms of VICM, but I need the equation for individual current ID1 and ID2 in terms of VICM. So for that, what I'm going to do is I'll take ID1 outside from equation number 7. I'm taking ID1 outside so that I will get the individual expression for ID1, and ID2 can be avoided by replacing that equation. What is ID2? ID2 can be written as GM2 VGS2, ID1 is GM1 VGS1. Okay. Please write ID1 is taken outside. So after taking outside, what will happen here? It will be 1 plus ID2 by ID1 is equal to right hand side appears to be same, that is VICM by RSS. Now I need to discard these two. I'm going to replace these two parameters. I don't want any ratio between current. I need it in the terms of transconductance. Okay. So I'm going to write an equation for ID1 in terms of transconductance as well as your input voltage. So I need to replace this ratio. Already you have computed this ratio. What is that ratio? ID2 by ID1 is given by GM2 by GM1. So substitute that. ID2 by ID1 is equivalent to the ratio of the respective transconductances. What is GM2, GM1? GM2 is the transconductance of Q2 and GM1 is the transconductance of Q1. They are not identical. They are having a few mismatch. Either it will be 1% or it may be 2% like that. So a finite mismatch is happening between GM2 and GM1, and this mismatch is going to affect our CMRR. That is what we are going to find out. Okay. So what is ID2 by ID1? From the previous analysis, that is as per equation number 3, we have ID2 by ID1 as GM2 by GM1. So substitute GM2 by GM1. Then you can take the LCM. Okay, simplify it, make it as a common denominator. Clear, students? Make it as a common denominator, rearrange it and find the equation for ID1. So bring this to the right hand side, rearrange it, take reciprocal and find the equation for ID1. Don't sit idle, take your notes, start practicing the derivation. So this is the expression for ID1 in terms of what? In terms of GM1, GM2 and your input VICM as well as RSS. Okay, put it in a box, let it be like that. Now we can go for ID2. Similarly, I need to find the expression for ID2 also. So for that, what you have to do? The same procedure, that is instead of taking ID1 outside, now you will take ID2 outside from equation number 7. Take equation number 7 again and take ID2 outside and proceed. So if I'm taking ID2 outside, within the bracket, you will have ID1 by ID2 plus 1. RHS remains same, that is VICM by RSS. And what is ID1 by ID2? It is the ratio between GM1 to GM2. So ID1 by ID2 can be written as GM1 by GM2. Are you following me, Banu Prakash?
Yes, sir.
Yes. Rohan? So the ratio between ID1 to ID2 is GM1 by GM2. Again, take LCM, make it as a common denominator. So the equation will become ID2 is equal to, rearrange it, ID2 equal to VICM into GM2 by GM1 plus GM2 into RSS. So now you got two equation number 8 and 9. That is the individual expression for ID1 and ID2. So please try to understand that the transconductance of the individual transistors, they differ by a very less amount. Okay, maybe 0.1%, 0.5%, 1% or like that. Okay, so need not necessary that if you take identical transistors also, their transconductance cannot be same. There will be slight mismatch. Okay, so what I'm going to do is, in the denominator, if you observe the equation for ID1 and ID2, in the denominator, you are having a term GM1 plus GM2, right? To take the denominators of the individual expressions, equation number 8 and 9, you are having a term called GM1 plus GM2. So in that particular term, we are going to replace it with 2gm. So this particular term, we would like to replace it with the 2gm because we are not going to take the effect of mismatch on the denominator because we are having a sum term, right? Okay. So the individual term gm1 or gm2, whatever it is retaining in the numerator, that we will keep as such. But the denominator term, that is a sum of gm1 and gm2, if you are summing together, it will be approximately equal to 2gm only. Because there is a slight mismatch between gm1 and gm2. It is not a big mismatch. Okay, even though we are taking identical transistors, we may not be getting exactly same transconductance. There is a very slight change. So the denominator can be now approximated as gm plus gm, which is equal to 2gm. But numerator, let it be as such, gm1 and gm2 according to equation number 8 and 9. Okay. So applying this logic to equation number 8 and 9, rewrite it. So ID1 will become VICM GM1 by 2 GM RSS, and ID2 is VICM GM2 by 2 GM into RSS. Students, now you got the individual expression for ID1 and ID2 in terms of the corresponding transconductance, the input voltage as well as the resistance. Okay. Now we need to find the gain. To find the gain, what we need to do, we need to find the output voltage. And what is the output voltage? It is taken in the double-ended mode. So we have to find V02 minus V01. Double-ended mode means the differential output. And according to our logic, your output voltage is given by VDD minus IDRD. But as per the small signal analysis is concerned, we have replaced VDD with ground voltage, right? That is 0 volt. So the signal voltage at the drain terminal is given by minus IDRD. So for Q2, it will become minus ID2RD. For Q1, it will become minus ID1RD. We have discarded the supply voltage. The supply voltage will not come to picture in case of the small signal analysis. That will be considered as ground. So after writing V02 and V01, take the difference between the two terms. So V02 minus V01. Therefore, the equation will become minus ID2RD minus minus ID1RD. That will become plus. Minus of minus will become plus. So minus ID2RD plus ID1RD. Take RD outside. So within the bracket, it will become ID1 minus ID2. Clear? So now you got the expression of your output voltage. Which output voltage? Differential output voltage in terms of the respective currents. And if you see this equation number 13, you have ID1 and ID2, right? And already we have computed the equation for ID1 and ID2 as per 11 and 12. Substitute 11 and 12 in 13. Substitute 11 and 12 in 13 so that I will get an equation in terms of input VICM. Why you are doing like that? Because I need to compute the gain. Gain is nothing but the output by input. Output is V02 minus V01. Input is VICM. So I need to replace the current in terms of input voltage. So for that only, I'm going to replace ID1 and ID2 in terms of VICM. Is that clear, students? Clear or what? Is that clear?
Yes, sir.
Yes, after substituting, take VICM outside. Take VICM outside. And what is this GM1 minus GM2? GM1 minus GM2 is the change in the transconductance, which can be written as delta GM. Okay, so this term can be represented as delta GM. So take all the common factors outside. What are the common factors? You can see RD, VICM is common. 2GM is common, RSS is common. All these are common, right? And within the bracket, you're having only GM1 minus GM2, and GM1 minus GM2 is nothing but delta GM. Now to find the gain, we need to find the ratio between output and input. So take VICM to the right side. So after taking VICM to the right side, your equation will become RD by 2GM into RSS and delta GM, of course. So RD by 2GM into RSS, and in the numerator, we are having delta GM. Rearrange it in such a way that delta GM by GM will come in a separate bracket, because this is the relative change in the transconductance in a percentage or in a fractional form. So equation number 14 represents the common mode gain. Now to find the CMRR, we need to compute one more parameter, that is the differential gain. Since we are interested to find the double-ended output, AD is given by minus GM into RD. Don't take half GM into RD. Half GM RD is applicable only for single-ended case, whereas GM RD is for the double-ended case. Please note that differential gain for a double-ended output is double or twice as that of the single-ended output. And while finding the CMRR, you should find the magnitude of ratio between AD to ACM, that is differential mode to common mode gain. So now I need to consider the negative sign. So GMRD divided by this ratio, this parameter. Okay. So divide GMRD by RD by 2RSS into delta GM by GM. So what and all things you have cancelled? RD can be cancelled, right? And RSS, 2RSS will come to the numerator along with the GM. So the numerator will become 2GM into RSS. So this 2RSS will come to the numerator and RD will get cancelled. So the numerator will become 2GM into RSS divided by, and in the denominator you are having delta GM by GM. Now what is this delta GM by GM? It is the relative change in the transconductance. Relative change in the transconductance. Relative means GM2 minus GM1 divided by the original value, that is GM. Clear, students? So this is the required CMRR. Okay. So normally the desirable value of CMRR is infinity. But the thing is, if this change is dominant over here, if we are getting more change in the transconductance, then CMRR will come down. It is inversely proportional, right? So if delta GM is large, delta GM means it is a change in the transconductance between Q1 and Q2. Even though we are taking identical devices, their transconductance may differ. And if that difference between the transconductance is very large, then subsequently this denominator is going to increase, and correspondingly CMRR will decrease from the infinity to finite value. And considering the ideal case, if there is no change means delta GM will be 0. No change means the transconductance change is 0. So the denominator will be 0. Anything by 0 will become infinity. Clear? So from this final result, we can really make out the difference between the ideal case and the non-ideal case. Non-ideal in the sense, if there is some mismatch in the transconductance, CMRR will come to a finite value. Otherwise, if there is no mismatch, there is no mismatch means delta GM is 0. If delta GM is 0, CMRR will become infinity. So based on this analysis, now we'll do one numerical problem. Take down the problem. A MOS differential pair operated at a bias current of 0.8 milliampere. Take down this parameter, capital I, as 0.8. So this is the total bias current of a differential amplifier. So capital I, which is the sum of the individual drain currents, ID1 plus ID2. So capital I is 0.8. Aspect ratio is 100. There is no change for the aspect ratio. It is 100. W by L is 100. Kn dash, mu n into COX is nothing but Kn dash, that is 0.2 milliampere per volt square. RD is 5 kilo ohm. RSS is 25 kilo ohm. And we are going to find the CMRR of this particular differential amplifier. And it is given that we need to take the output in a double-ended way. That means output is taken differentially. That is, it is a double-ended output with a mismatch of 1% in GM. So 1% mismatch in GM is provided. Based upon that, we should find the CMRR. So it is not the ideal case. We might have taken the same drain resistance as specified 5 kilo ohm. That is fine. We might have taken the same transistors with same aspect ratio 100. We might have taken the devices with identical Kn dash value. That is also fine. But unfortunately, their the trans conductance is different, and it is differed by a 1% mismatch. So accordingly, we need to compute CMRR. So anyway, CMRR is not going to be infinity. It will be a finite value. So before proceeding, first of all, we should find GM. Because why we are finding GM? As per our analysis, the CMRR is related to GM, right? So to find GM, you need to find the overdrive voltage. So for a differential amplifier, the overdrive voltage VOV is given by I by Kn dash W by L. Substitute for capital I and Kn dash and W by L. Everything you need to substitute and find the overdrive voltage. After finding the overdrive voltage, find the ratio between I to VOV. That will be your GM. Since I is also in milliampere, right? Retain the same value so that the transconductance can be milliampere per volt. No need for conversion. Okay. 0.8 milliamps means your transconductance will be in milliampere per volt. So you will get 4 milliamps per volt. After finding GM, substitute here. RSS is also given 25 kilo ohm. And what about this? Mismatch is 1%. Mismatch 1% means delta GM by GM is 1%. That is 0.01. 1% means 0.01. Delta GM by GM is 0.01. So substitute all the three parameters and get the value of CMRR. Then convert into dB scale. So whenever you are computing CMRR, convert into dB scale by taking 20 log of that particular value. All of you put your answers in the chat box. Yes, 20,000. The answer is 20,000. So we can't expect infinite CMRR because since there is a mismatch in transconductance, CMRR will come down to a finite value. Now convert into logarithm, I mean dB scale, that is 20 log of 20,000, that is 86 dB. Clear? Students, today what you have learned is the mismatch in GM. How the mismatch in transconductance is going to affect our CMRR. Okay, so you need to derive this. So this is very important, effect of GM mismatch on CMRR for your SCE and CAE. Okay, and the numerical problem is also very, very, very important. So you can expect a sure question from the effect of mismatch in drain resistance or effect of mismatch in transconductance. Either one will come sure for sure, either numerical or that derivation. So kindly practice it. Okay. So now we have only two more topics to left. I think we will continue the same from Monday onwards. So whatever I'm taking on Monday, Tuesday, that will also be included for your CIE. And by end of the day today or by tomorrow afternoon, I'll update the question bank as well as the notes and the recordings in our YouTube channel. You can make use of that and practice. And I'll share the attendance link. So the link will get deactivated within 5 minutes. The link is available in the chat box now. Can you see the chat box and let me know? The attendance link is visible for you, students.
Yes, sir.
Okay. Okay, once you mark the attendance means you can leave the meeting. We'll continue on Monday. Once you enter the attendance, you can leave the meeting. Then I'll close attendance link also. Neeta, Rakesh, Rishik, Varun. If you're there in the meeting means you can mark the attendance and leave. Vaishak, Tanmaya.